what is Optiver? So how many of you have heard about Optiver before you came over here tonight? Of course, other than Optiverians, probably not too many. Oh, great to know some. Yeah. So many of you probably first time heard about Optiver. You look at our website. So what does it say? We are an electronic trading firm. We trade financial instruments such as futures, options, stocks, ETFs in exchanges across the globe, more than 50 exchanges. And we're a market maker. But what does a market maker mean? That means we always provide both the buy and sell price on the exchange. And we're always waiting to trade regardless of market conditions. So that may be still a little bit of a abstract. So let me give you 2 examples. So first example is when the market is very volatile. For example, after a US election, there could be many of the market participants want to pull out because of the volatility. And that's when our market makers come in. So maybe a pension fund manager want to pull out their assets, but we can be there to partner that trade, to be on the other side of that trade. The second example will be when the market is very quiet. So you may have some of the instrument that is not much activity, so the buyers and sellers of that instrument may not come into the market at the same time. And that's when, again, a market maker comes in to provide that buy and sell price and always willing to be the partner of that trade. We are committed to improve the market. That means we provide the liquidity, and we help with the price discovery, and we bring the transparency and efficiency to the market. So that, in short, is a market making. But what does it take to be a successful one? There's mainly 2 aspects where we really focus on. First one is pricing. Is how do we price our financial instrument? How do we provide the best price on the market? We have a small army of researchers with their mathematical equations trying to figure that out upstairs. The other aspect is speed. Speed has always been very important for market makers. Even in the old days with open outcry, speed means that you are the first one, the fastest one who can calculate those numbers in your head and shout it out. These days, in a state-of-art electronic trading platforms, that means that our algorithms, our trading algorithms, our computer systems have to be very, very fast. So there's many aspects of our business won't have questions about price and speed. And here are some of the examples. Which of our trading strategy is winning, and by how much? Where is the next business opportunity that Optiver can provide the best price and still be competitive? Are we complying with regulations in terms of our pricing and in terms of our competitiveness? And this exchange upgrade could be just purely technical thing, but did they increase or decrease the market fairness? So at Optiver, we aim to make data-driven decisions. And to answer those questions, we need to have data to back it up. And that's where my teams comes in. As the infrastructure data team, we provide this data through network capture. So how do we do it? First of all, let's say there's an exchange, that's the electronic trading platform. For Optiver, we have our services, our servers, co-located next to the exchange, where we have direct connections, network connection to the exchange. And my team start from here. As is taking that network connection, we actually physically split the light in the network wire. We take a small chunk of that, and then we push that into our aggregator device. This is where we timestamp every single network packet on the ingress of that device with nanosecond precision timestamps. Then we forward that timestamp data into our capture server and persist that into disk. So this is the capture part. Next step to provide that data into the business is our data processing pipeline. We deduplicate the data, we normalize data, we compress data, and then we store that into a time series database. And from there on, we build a Python, C++ API, and provide also the GUI on top of that for the users to be able to quickly query this network data. So before we talk about the quality of the data, the first challenge we have for this project is actually the quantity of the data. So how much data do we actually capture? The biggest moment, very, very short, 10 seconds, let's say, is around the US market open. That is 8:30 in the East Coast time, US, or 3:30 at this moment, local time. We capture 35 million packets per second across the globe. We capture totally of 10 terabytes of data per day. And after processing deduplication, we have about 1 terabyte of processed data. And 70% of that, we persisted indefinitely. Another way to look at the data volume is to look at a single exchange. So at Eurex, which is the largest futures and options market in Europe, we trade Eurex, the futures and stocks, and futures and options. On a very, very quiet day, we have about 1,500 network connections to the exchange. We receive 2 billion packets on the day. And within the packets, there are multiple market events, and that's about 4.3 billion market events on the particular day I was looking at. So big numbers, what does it mean? Is really, what I'm hoping is to show you a little glimpse of how busy those new generations of electronic trading systems is. So to be able to handle this amount of data in a very, very short period of time, that means our systems, our whole trading system also need to react to them very, very fast. So when the market comes in, we need to be as fast as possible to calculate a new price and as fast as possible to put that out onto the market. So at Optiver, we say every nanosecond counts, and we really mean it. At the certain scenarios, sometimes when we do an iteration of improvement for our trading systems, it really comes in handful of nanoseconds. And if you want to measure that, have an accurate measure of that improvement, that means your measurement need to be below the nanoseconds. And that's where the business requirements comes in. But before we dive into the nanosecond, I would like to ask all of you a question. How long is a nanosecond? So first of all, blink of eye is around 300 milliseconds. And that's also about time where in terms of UI design, they will say anything below 300 milliseconds, human will not notice. But how about the time for your browser to reach Amazon DE, the website? Assuming that they host it in Frankfurt, Germany, in their data center, the public internet speed is about 16 milliseconds. And that's still way, way longer than a nanosecond. And if you stand below the Eiffel Tower, look up to the tip, how long would it take? I think that's where your calculation comes in, because that is the speed of light travel in air. That's about 1 microsecond. That's still 1,000 times longer than a single nanosecond. And I brought this cable here. That's a 1 meter of network cable. And that's about 4.9 nanoseconds. So the light travels in those kind of devices about 66%. So basically, 1 nanosecond is about this much. And that's the scale we're talking about. So now we know, roughly, have some kind of visualization how long a nanosecond is. So how do you capture it? How do you measure that? Of course, you need to have good devices. So our last generation of time-stamping devices, we have a 3.85 nano precision. And that's where sometimes that could be even, the precision even is bigger than the actual performance improvement we want to measure. So last year, on the market, finally, we got some new devices where they claimed sub-nanoseconds precision and accuracy. So we get a few, and we want to see whether it really does what it does. So we put it into the lab, and we did an experiment. We take a single signal, network packet. Let's say we produce a single network packet. We put it onto the network wire. We again split the light equally, and from their equal distance cable into 2 ports of this device. And they're being time-stamped at the ingress of the ports twice. So ideally, with everything equal, you should get exactly the same timestamp. But of course, in reality, you don't. So we compare the differences between the timestamps. And what we can see is actually very interesting. First is that we see a normal distribution. So in general, we see a distribution of about 150 picoseconds wide. And this actually matches really well with the 75 picoseconds accuracy because there are 2 measurements we're looking at. The second thing interesting about that experiment is that we can see the values are discrete. And between the discrete values, it's actually exactly 15.125 picoseconds. That's their precision of the measurement. So, yeah, they did what they claim they can do. Also, another very interesting observation we got was that there's actually a slight offset of that difference from 0. That means one of the port, in general, have a timestamp that's earlier than the other, about 10 picoseconds. And that difference is actually attributed to the design of the device itself, of the circuitry of the device. So we're really talking about a few centimeters difference inside of a circuit. Luckily, we can actually measure those differences within each port and then be able to statically correct them. So we have now a good device, a very accurate, precise device to measure the thing we want to measure. But there's only 48 ports on it. What happens if we want to scale it up? We need to have multiple devices. But multiple devices come into a new problem. What is the real time? How do you compare the timestamps from multiple devices? They each say, I think right now it's 1 o'clock. Another one says, I'm thinking it's maybe 1:01. So which one is real? And how do you compare the data? So that comes to the second challenge we have for this project. Means if we want to really be able to compare the timestamps between the devices, they really need to be in sync. But to do that is actually not so simple. The first thing is, so this is something we actually observe while we putting those new devices into our production. We actually, in one scenario, we have one signal that's captured by 2 devices. But those 2 devices actually synchronize to a time source differently. And so what we see here is that the difference of the time source can be 2,000 nanoseconds apart, while we're trying to measure something sub-nanoseconds, so it doesn't really make sense. If you don't solve the time synchronization issue, your data is useless. So through lots of research and trial and error, we kind of concluded there are 2 aspects of the time signal distribution that's very important for our project. The first one is the source. So you need to have a very, very stable source. It doesn't necessarily need to be the correct absolute time. There's no real absolute time, but it needs to be very, very stable. So we start with the GPS. So across the globe, the GPS claims that they can do about 20 nanoseconds difference from all the different clocks. And within GPS, they have a clock module, atomic clock module, where you can track time very, very accurately. And from there, we get a GPS signal. Then we use a technology, or say a protocol called the pulse per second, to transmit that signal, the time, into our devices. So 1 second, 1 pulse per second, very, very, very sharp pulses. And from there, then the device knows the time. This is the beginning of a second. But within that second, then it has its own internal atomic clock to track the progression of time. And that's how we have set up our devices to make sure there's least amount of jitter possible in our time measurement. The other aspect of getting the time distribution correct is the distribution method itself. So it's actually very difficult to distribute the PPS signals in long distance. And here, in one of our co-locations, we actually partner with the exchange that use a technology called the White Rabbit network. So yes, it's a black rabbit, but the actual devices look like this. The technology actually developed by CERN, because they also have a requirement to synchronize thousands of devices, measurement devices, across a very, very long distance, like 10 kilometers. And the technology itself claim of sub-nanoseconds accuracy for synchronize those devices. So here we get we use the White Rabbit network from the exchange that's being distributed across the whole data center. And within our own part of the data center, we'll then use a local PPS distribution unit into our devices. And there we also even measured every single cable that we use from the distribution unit to the timestamping devices to make sure that we can offset any differences in terms of centimeters to make sure that our time distribution is correct. So after a whole year of hard work, this is what we got. So we have 10 devices of such devices in one of our most important co-locations. And we can see is that we were able to synchronize all those devices within 2 nanoseconds of each other. Or pairwise is actually really below a nanosecond. That means now we can measure everything that's captured by those devices. We can compare them knowing that they are not more than 1 nanosecond apart. So if you're really interested in this part of technology, I also recommend you to have some additional reading. So there's other uses for this type of technology in the financial markets. So this is a case study by the vendor of the device with the exchange, partner with the exchange. They use this setup to be able to actually monitor the market fairness. They can take a look at whether their market distribution is fair and whether the participants are behaving fair. So a little bit of extra reading material if you really like the topic. Other than the first two challenges I've mentioned about the precision and accuracy, about the time distribution, there are some other data engineering challenges that's quite peculiar for Optiver and for the data, this particular project. First is that to capture network data, we actually have a very predictable bursting behavior right around market open. It means that for capacity planning, we actually need to really have to double that peak amount, and then for all our locations, even though majority of the time, the device is sitting there like doing 10% of the time, 10% of work. And it's also with this type of setup is that you cannot use the additional capacity from one place to another. It really, when market gets busy, it gets busy at the same time, globally. The other challenge that's kind of maybe more of an Optiver thing is the capacity planning or the lack of planning. Our business moves really, really fast, and our organization is very agile. So last year, we had a case where within a short month, we have to triple up our capture capacity in its co-location. And in the particular case, we simply have to scrape up all the devices we have in the lab and put it into production. But we did it quickly, and then we got the data needed for the business question. Another more towards the software side of the things, of the challenge for this project is actually when you start capturing and storing and using the picosecond data, you find the tooling with the picosecond support is very spotty. So, not sure if you're aware, but if you store the time series data in a database, in general, you use the timestamps, the nanosecond timestamps, as the primary key for the database. You can fit a nanosecond timestamp into a unsigned 60-bit integer that can last you to 25 something years. So from epoch. So you have plenty of time. So let's say, with our working time is fine. You can put a nanoseconds in there, no problem. But you cannot do that in picoseconds. If you put just picoseconds from beginning of day, you can capture about 200 days of data. Then you need to start to reset. So of course, there's many ways to solve that, but none of them is simple. So one is that you could try to increase your primary index to a bigger field to have more bits. But the tooling, that means you need to change all of your tooling and then change your old data and everything. So it's very messy. You could also try to add a second field to even try to, adding just the picosecond part, but that also means anytime you want to join a time series data, trying to find the beginning and end of the data, trying to merge the data, every single time when you're trying to look at your primary index, you have to handle the second one as well. So the support is there, it's doable, but it's simply just not well tested in many of the tools we use. But that is somewhat a solvable problem. I think through time, we will get a better handle of that. So that conclude my talk for tonight. We discussed a little bit about what Optiver does and why, what it means to be a market maker. We talk about what my team does in terms of capturing this data to answer the business questions. There's lots of technical details there, and some of them maybe interest you, maybe not. But I think what was interesting for me is that while I was preparing this presentation, I realized I didn't know any of that when I joined Optiver 5 years ago. And for me, this presentation is kind of my journey at Optiver, where I really felt like I learned lots of new things and also had lots of fun. So that's what I hope I did with this presentation, that you learn something new, you find some exciting new technologies, and you also had some fun. So thank you for your time.